Hello, and welcome to Empowered Learning. This particular lesson will be on employing the chain rule when doing the derivative of functions. When we do the chain rule, what we're really trying to do is say, I need to take the derivative of a composition function, and I need a strategy for how to do that. And so what the chain rule does is give us a strategy for how to take the derivative of composition functions. When employing this particular strategy, there's two different ways that we can do it. We could do it using what we call prime notation as well as Lebanese notation. So I have both shown here, and I'm going to go through those. And as we do these problems, I'm going to do each problem two different ways so that you can see how it looks in either form of the chain rule. And so you can choose which one will work best for you. So here we have some function h of x, which is made of the composition of two other functions, f and g, where g is our inside function and f is our outside function. Then when we take the derivative of that particular function, then what we're doing is we're taking the derivative of what we call the outside function with respect to the inside function looked at as a variable times the derivative of the inside function with respect to the original independent variable. Okay, so in short, we just say derivative of outside function times derivative of inside function. And so there's a lot of implied information that's there that we'll use whenever we're employing this form of doing the chain rule, which is called prime notation. Now for Lebanese notation, we explicitly write out what we're going to take the derivative of with respect to what variable, okay? And so here you see that I have the derivative of h written in terms of x, but here you see now if I allow my inside function, which is g of x here, to be substituted by u, then we could rewrite the derivative of h with respect to x as dh over du times du over dx. And so you see these two du's, they reduce to 1. So this expression and this expression, algebraically speaking, are equivalent. So notice I also have this written in terms of g here, because we know that u is equal to g. And so this is what's called the Lebanese notation for it. And whenever we employ this form of it, we're explicitly writing out what variable we're going to take the derivative with respect to, which means there will be some side work on taking certain expressions within a problem or certain inside functions within a problem and actually explicitly saying what that is and assigning it another substitution variable. Okay, so for some problems, doing the Lebanese notation may be a little cumbersome, and other times it may fit perfect. Versus prime notation, if we have a lot of inside functions, we may lose track of what to take the derivative with respect to. So again, there are times when you want to use prime notation, times where you want to use Lebanese notation, and I'll leave that up to you as to when you feel like you need to do both. I'll just show you both ways and you can make that decision on your own. All right, so let's look at our first problem here. So our first problem, we have y is equal to cube root of 3w minus 7. And we want to take the derivative of that. So we notice here that this is a composition function because the outside function is cube root of x and the inside function is 3w minus 7. So we know that we're going to be employing the chain rule here. Now to make life easy for ourselves, since this is in root form, we can turn this into something raised to a fractional exponent. So here we could rewrite this as 3w raised to the 1/3 power. Okay, so looking at that, now when we have to take the derivative of this, we know that we can use the power rule when doing it. So let's say we know that we take the derivative of y with respect to w, and this could be written as y prime of w. And so we'll take the derivative of what's called the outside function. And so the outside function looks like x raised to the 1/3. So if we took the derivative of that, that would be 1/3 x raised to the 1/3 minus 1, or minus 3/3. And of course, that would give us this. So we're going to write this there, but instead of x being there, which is what we know the variable to be in this case, our variable is 3w minus 7. So we will write this as 1/3 times 3w minus 7 in place of the x, all that raised to the 2/3 power. And so that's how we take the derivative of the outside function when doing that. So now we've taken the derivative of the outside function. Now let's take the derivative of the inside function. And so for clarity, I'll just denote that as taking the derivative of 3w minus 7. Okay? So if we look here, the derivative of 3w is just 3, and the derivative of 7 is 0. So if we look at all that, this whole thing just ends up being 3. And so now when we simplify, we have 3 times 3w minus 7 raised to the negative 2/3 power. And of course, these 3's reduce to 1, and we end up with 1 over 3w raised to the 2/3 power. And we could rewrite this, putting it in the same form that we had here, this way. Okay, so this would be our answer to taking the derivative of y with respect to w using prime notation. So now I'm going to erase this, and now we'll do the same exact thing, but we'll do it using Lebanese notation. Okay, so in Lebanese notation, we start off saying the derivative of y with respect to w, but now we're going to call the inside function something else. So I'm going to call it z this time. So I'm going to say let z equal 3w minus 7. So now, according to what I have here, I'm going to write the first part of this, the derivative of the outside function, with respect to my inside function variable, which it's u here, but in this case, it'll be z. So when I write it, it'll be dy times dz times dz over dw. And you see how that mimics here. We had the h that came from here, but now that's y. We had the u that came from here, but now that's z, okay? And so now we just fill everything in. So we have d over dz of y, and our y is going to be, if we write this out, then our y now is going to be z raised to the 1/3 power. So that will look like that, because again, if we take this and replace it with z, that's what it looks like. So that's how we know that this part here is going to be z to the 1/3 power times derivative of z here, and z is just 3w minus 7. Okay? And so now, when we come and do it this way, we know from last time that the derivative of 3w minus 7, all that is just 3. And when we do this, this would be 1/3 z raised to the minus 2/3. And then, of course, we append the minus, the 3 there. Append the times 3. Of course, 1/3 times 3 gives us 1. So we end up with z raised to the negative 2/3 power, which, of course, will be this. And now, to finish off, what we end up doing is we substitute back in what z was. So z was 3w minus 7. So when we come, this is 3w minus 7. And of course, that's squared. And you see we get the same exact answer as we did last time. So you've seen question A done both prime notation way as well as the Lebanese notation way. So now I'm going to erase all this and we're going to work on problem B. All right, so for problem B, we see that we have natural log of x plus 1 divided by x cubed, and we want to take the derivative of this. If you notice, since we have a quotient here, we will be employing the quotient rule. And in your numerator, if you notice that natural log of x plus 1 is indeed a composition type function. We have an inside function, which is x plus 1, and an outside function, which is just natural log of blah, or natural log of x, if you want to say it in general. So we're going to be using a combination of different things here. So I'm going to go ahead and do this doing prime notation again, and then I'm going to turn around and do it in Lebanese notation. So doing prime notation, I know that since I have the quotient of two functions that I'm going to do the quotient rule, which is low times derivative of high minus high times derivative of low over low squared. So just going to write that. So we have low times the derivative of the high function, or the function in the numerator, minus high times the derivative of the low function, and all that over the low function squared. Okay? So when we do this, of course, we're going to write our x cubed as normal, but when we take the derivative of natural log of x plus 1, remember that we're taking the derivative of the outside function first with respect to the inside function. So we know that for natural log of, let's say, z, the derivative of that would be 1 over z. Okay? So when we take the derivative of the outside, this would just be 1 over x plus 1, because x plus 1 is acting as the variable. And so we multiply that times the derivative of the inside function, which is just derivative of x plus 1, of course. And we know that this all ends up being 1 here, so I'll go ahead and note that. So we go to the next step, then we need to just do natural log of x plus 1, we're not doing anything to that, times the derivative of x cubed. And we know that that is going to be 3x squared. Okay? And so we take all that, and then we know that the denominator is going to be x to the 6th now. So now that we have that in place, we can go ahead and finish everything up. So we've taken all the derivatives that we need to take. We just need to clean everything up now. So here we have x cubed over x plus 1 minus 3x squared times natural log of x plus 1. And natural log of x plus 1 is all one thing. And then all that is being divided by x raised to the 6th. And so if we break this up into separate fractions and divide this up into two separate fractions, we would have the following. Okay? And so then from this particular step, of course, we can do some reducing here. But what I'm going to do now, instead of reducing first, is I'm just going to find a common denominator. So here we have x plus 1 times x raised to the 6th, and we just have x raised to the 6th here. So to get a common denominator, I need to multiply this second term by x plus 1 over x plus 1. And of course, when we do that, we get x cubed minus 3x squared times natural log of x plus 1, all that times x plus 1. And we can put that all under one denominator now. Okay, so we're almost done with this one. So if we keep going, we notice here that both terms have at least two x's in it, or at least x squared in it. So if I factor out an x squared, then that leaves me with x in this term minus, and this will take out the x squared and leave me with everything else. So it'll be 3 times natural log of x plus 1 times x plus 1, and all that over x to the 6 times x plus 1. And of course, here we know that we have 2 x's here, 6 x's down there. So this will reduce, and that will change to a 4. And so our final answer just ends up being x over 3 times natural log of x plus 1 times x plus 1, all that over x to the 4th, x plus 1. And so this is what the derivative would look like if we were doing this in prime notation. So we're going to go ahead and erase this now and actually do the same thing, but do it in Lebanese notation. And I'm going to write our answer down here just so that we can remember it. Okay, so we're going to go ahead and erase, and we'll start this problem over again. All right, so to do this in Lebanese notation, we're going to say the derivative of h with respect to x, but now we need to see what our inside functions are and change that. So like we mentioned before, we know that the inside function for the function in the numerator is x plus 1. So what we're going to do here is let u be x plus 1. Okay, so if we do that, then that will replace the x plus 1 here. But now, since we're trying to change everything from a function of x to a function of u, we need to find a way to deal with this x cubed here. So here it turns out that if we subtract 1 from both sides right here, that u minus 1 will be equal to x. And so from that, we could rewrite x cubed as being just u minus 1 quantity cubed. Okay? So from here, we can say that h now can be written as natural log of u over u minus 1 cubed. And that would be the equivalent of saying it this way. And so we're going to use this when we need to take our derivatives here. So for Lebanese notation, we know that if we write this out, this will be dh over du times du dx. So we're going to take the derivative of h with respect to u, which we'll use this one, and then we'll take the derivative of u, which is this, with respect to x. So coming here, the derivative of h, which is derivative of all this, times derivative of u, which is just x plus 1. Okay. Now, of course, the easy derivative here is the second one, the derivative of the inside function. So the derivative of x is just 1, derivative of 1 is 0. So all this just ends up being 1. Whereas for here, again, we have to employ the chain rule. Okay? So when we do this, we have to do low derivative of high minus high derivative of low over low squared. So I'm going to go ahead and write that now. So low times the derivative of the high function minus the high function times the derivative of the low function and all of that divided by the low function squared. Okay. Now notice when we do this, our natural log of u, when we take the derivative of that, that will be fine. There's not much to that. But here, notice that we have another composition function. We have a function where u minus 1 is the inside function and blah raised to the third power is the outside function. So we're going to have to name us another variable here, okay? So when we come and do this, one of the things that we need to note, and I'll just put it here on the side, note, I'll erase this. So now I'm going to say let z be u minus 1, okay? So if we do that, then that's going to imply that if we look at this, this is now going to be the same as saying this with respect to z of z cubed. Because of course we're letting z be u minus 1, okay? So the derivative of this with respect to z, we just replace u minus 1 with z there. So taking that into account, we're going to go ahead and continue this. So I'm going to sort of bypass all this and then continue the problem. So we have u minus 1 cubed times derivative of natural log of u is just 1 over u minus natural log of u times, and now we employ the chain rule here. So here, if this looks like dz over du, but now we're going to do dz of dz times dz dw, and that's not right. So I think I lost my space here, so let me figure this out. So we're going to do it this way, yeah. We need to rewrite this as, that's where I went wrong. Yeah, we need to write it like that. So here we're not changing this z here. We're not changing this to z, we're just changing that. So we need to write it this way. And we take that, and this part here will be this raised to the 6. And so we'll go ahead and employ the chain rule here on this next step. So this is u minus 1 cubed over u minus natural log of u. And here we will rewrite this as d dz of z cubed, and then times du du dz. Yeah, so dz du, yeah. As you can see here with the Lebanese notation, for this particular one, it's kind of hard to keep track of everything. But again, I want to show you how it works. So we come here, and of course, when we write this, this will be d of z to the 3 over dz times dz du. So those dz's still reduce to 1, and we have the equivalent statement here. So that's what I was trying to remember right there, but just kind of got hung up there for a second. But anyway, we're fine. So moving on, we know that this z here, we said z was u minus 1. So I'm going to take this and put u minus 1 in there so that we can go ahead and take the derivative of it. So on our next step, if we come through, we'll see I'll rewrite all this other stuff. And so now we know that the derivative of z raised to the 3rd with this is just rewritten this way. So now we're here, and we'll take the derivative of z cubed with respect to z. That's just 3z squared. And the derivative of u minus 1, the derivative of u with respect to u is just 1. The derivative of 1 is 0. So all of this is just 1. So we multiply that times 1. And then we say divided by u minus 1 raised to the 6. Okay? So now at this point, what we're going to do is substitute back in all of the things that we've taken out. So for instance, we know that u minus 1 is the same as z. So we're going to see everywhere where we have u minus 1, replace it with the z. Everywhere where we see u was x plus 1. So here we have x plus 1. Everywhere where we have a z, if we look, z was u minus 1. So all this is just u minus 1. So when we go and replace everything, it's going to look as follows. And of course, we know z here is the same as u minus 1 as well, which is the same as x. So all this gets replaced with x. And so again, we had u minus 1 here and here. U minus 1 is z, okay? And so we also note that u minus 1 was also equal to x. So of course, our original function had its independent variable in terms of x, so that's how we want to leave it. So x, we have x plus 1 here, and of course u minus 1 is equal to x as well, so we'll take this out and put x there, okay? So now that we have this, have one more u, this is x plus 1, so we have x cubed divided by x plus 1 minus natural log of x plus 1 times 3x squared, and all of that divided by x to the 6 times x. Oops, x to the 6. That x goes here actually, okay? So again, this was u minus 1 cubed divided by u, in which we know u minus 1 is the same as x, so now that's x cubed. U is the same as x plus 1, so that's why we put it there. This was natural log of u, but now we know u is the same as x plus 1, so we replace that. We know z was the same as u minus 1, and u minus 1 was the same as x. So we replace that with x here, and then of course we had u minus 1 here raised to the 6, so u minus 1 is x, so that's x raised to the 6. And so now we're getting to the grand finale here. So of course, if we write this out as two separate fractions, then we'll get the following. Okay? And so from here, to make like terms, we'll need to multiply the numerator and denominator of the second term here by x plus 1 divided by x plus 1. Okay? So in doing that, we have, it's looking this way. Okay? And so, of course, if we combine everything together, make it one quotient, then it'll just look like this. Okay? Now notice here again that we have at least x squared in both terms, so we could factor that out. And we just have x left in the first term. And natural log of x plus 1 times 3 times another x plus 1 left in the second term. All that times x raised to the 6 times x plus 1, all in the denominator. And of course, just like how we did last time, we know that this can reduce to 1 over x to the 4. And as you see, we end up with virtually the same thing. Okay? Of course, this says minus 3 times x plus 1 times natural log of x plus 1, and I just have that flipped around. Okay? So if we were to write that the other way, of course, it would look like this. And we would have the exact same thing. All right, so I know this particular problem was a little long, but the thing is, I wanted to show you that this can be done by Lebanese notation. And so to me, this is one of the ones where it's kind of hard to actually do the Lebanese notation and keep track of everything, because it is easier to actually just do the prime notation for this one. And you kind of saw that as I got lost a little bit in defining of the variables and whatnot. But, you know, it is possible and you can work your way through it. Okay. All right, so for our last example, go ahead and erase this right quick. All right, so for our last example, I'm going to go ahead and move this one up. I promise this one is easier. So for this, we have f of x is log of base 2 of 3x squared minus 1. Okay? And so to finish this up, we see here that we're going to take the derivative of this. So I'm just going to do this in prime notation to start off. So prime notation says take the derivative of the outside function with respect to blah. So when we do this, the derivative of log of some base here is just 1 over x times natural log of whatever the base was. So when we do this, this will be 1 divided by, and then our x here is actually 3x minus 1, because whatever's here has to go here. So all of that is inside a parenthesis, so that has to be there. So we do all that times natural log of 2, because that's what our base is. So this is the derivative of the outside function part. And so now we're going to say that times the derivative of the inside function part, which is that. So now derivative of the inside function, if we look at this on the next step, we see that the derivative of 3x squared is just 6x, and the derivative of 1 is 0. So all of this is just 6x, and of course we can put that in the numerator there. So This pretty much concludes this particular problem using the prime notation because we can't really simplify anything else beyond this point. So again, you can see that using the prime notation for this was fairly simple to do. So now I'm going to erase and then finally do the Lebanese notation for this one. All right, so doing Lebanese notation, again, I'm going to do substitution. So I'm going to say let u be my inside function, which is going to be 3x squared minus 1. So from that point, we know that f can now be rewritten as log base 2 of u. And so if we're going to take the derivative of f with respect to x, that will be the same as taking the derivative of f with respect to u times du dx. And so here we say d over du, our function f is actually going to be in terms of u here, written like this. And now we have the derivative of a function with respect to x, and we know that u here is going to be 3x squared minus 1. And so now we just take the derivative of log base 2 of u, and so that will be 1 over u times natural log of 2. And of course here we know from last time that the derivative of 3x squared is just 6x. And so to simplify everything, we can put 6x in the numerator, and we know that u was 3x squared minus 1. So we substitute that back in, times natural log of 2. And you see that we still get the same answer no matter how we do it. Okay? So the next thing that we're going to do here, and I'm going to make another video for this, is to continue this, but now we're going to apply doing the derivative of functions where we have to use the chain rule in order to find the equation of a tangent line, or we need to find out where our function actually has horizontal tangent lines. So that's what we'll do in the next video.